Hello there, everyone. We are back with the central limit theorem. This one is actually huge. And this first page that I have here for you is a lot of the theory behind it. I'm not going to get too in-depth with it. What's going to happen with the central limit theorem is our standard deviation is going to change, and it's going to really make it spike, meaning the walls are kind of closing in down here. So all of the good information is getting closer and closer and closer to the mean. And the way we're going to be doing that is we're going to be having a sample now, and we're going to divide our standard deviation by the square root of that sample. So this is going to be sort of the key figure here. Our mean we're going to assume is the same. And our new standard deviation is often called the standard error of the mean. And that brings us to the highlight of this particular section called the central limit theorem. So regardless of the shape of the underlying population, the sampling distribution x bar becomes approximately normal as the sample size n increases. So basically that means the larger n, the more normal it is. A couple of things to keep an eye on as we're looking here. If the distribution is unknown or not normal, then we need at least an n size n is larger than or equal to 30. And if it is normal, then the n is irrelevant. It can be smaller or bigger than 30. It does not matter. We can still use this theorem. Now, basically what our practice is going to look like is here. So I'm going to do some things sort of in the abstract more, and then I'll do some more concrete examples. Hopefully that'll kind of hammer it down a little bit. So for our example, suppose a simple random sample of size n equals 36. You'll note that is bigger than 30. So that's good for us. This is obtained from a population with a mean of 82, standard deviation of 6. So we're going to describe the sampling distribution of x bar. X bar is approximately normal, meaning a normal distribution, because n is 36, which is bigger than or equal to 30. Now, this is a mu sub x. That stays the same. If you remember, that is going to be the same. So this is still 82. But our new standard deviation is not. We're going to take our standard deviation, which is 6 in this case, and I'm going to divide that by the square root of n, which is 6 over root 36. Root 36 is 6, of course, so 6 over 6 is 1. And once again, this is called the standard error of the mean. Standard of the mean. We are going to try to sketch these two. So here is x. And then we are at 82. This is where sigma equals 6. And we have, I'm going to use the 84 from here in just a moment. And when we're here, we're still at 82 here, but here's sigma sub x bar is 1. We calculated that up here. And what is p of x bigger than 84? Well, that is here. 84 is here. Well, this is going to be norm, CDF, because we're looking for area or probability of 84 off to infinity with a mean of 82, standard deviation of 6. That gives us approximately 4, comma 99999 comma 82, comma 6. That's this one. But this is x bar, meaning we now have a sample involved, and that's going to change things. Specifically, it's going to change the standard deviation. And we'll see what that does here in a second. Let me mark up this picture just a little bit. So now 84 is here, and you can see that's a lot less area. Than that's going to be, if my pictures were drawn better. So now, (84, 999, 82, 1 now. And you can see this drops a lot. And the larger the sample gets, the lower it drops. So now we're going to go an in-between here. This is going to be normal CDF. 81.2, 83.75, 82, and 6, pardon me. This is x, not x bar. So this is going to have a lot of the middle stuff here. So I don't want to draw on this one, but that's going to be right next to 82 in there. So that's going to be a really small sliver. Whereas if we're here and here, you can see the vast majority of that is going to be in the middle there. So I expect this one to be a lot lower than this one. So here we go. I got 0.1678. Whereas this one, normal CDF, this is going to be dramatically larger, I'm guessing. 81.2, 83.7, 82, and then now our standard deviation is 1. And you can see that is huge compared to the other. Once again, that makes sense. If I'm cutting it off here, all that area, there's a lot more there than if I'm cutting it off on this tiny little sliver here. Because you can see 81.2 and 83.75 is very close to 82. So it's going to be a very little area there, whereas that's going to be a lot of area there, the vast majority of it. All right. I'm going to do the second example first, actually. I think it's a little bit more concrete. So the amount of time adults spend watching television is closely monitored by firms because it helps to determine advertising pricing for commercials. According to a survey, adults spend 2.35 hours per day watching television on a weekday. Assume that the standard deviation for this on a weekday is 1.93 hours. If the random sample of 50 adults is obtained, describe the sampling distribution of X bar, the mean amount of time watching television on a weekday. So in this case, X bar is approximately, first of all, normal. And we know this because n is 50, which again is bigger than or equal to 30. And our mean stays the same. However, our standard deviation is not. We're going to take 1.93 and divide that by the square root of 50. Now, what I could do is I could store that number off into a memory, but what I'm going to actually do is put that directly into the problem. So once again, just real quick. This is 2.35. And they want to know less than 2 hours in a day. That is going to be about here. This is 2 and down. Well, here you can see, again, this is going to be normal. CDF. Lower bound of negative 99999. Upper bound of 2 with a mean of 2.35. And the standard deviation is 1.93 divided by root 50 because we have a sample. And I want to show you, you can put this directly into the calculator as is. So negative 99999, comma 2, comma 2.35, comma, and here we go, 1.93 divided by the square root of 50. So I put it directly in the calculator like that, and that gave us this here. Let me round it off. Yep, I put that in the wrong one. This goes down here. I jumped the gun here. This one should be without the root 50. Negative 99999, comma, 2, comma, 2.35, comma, 1.93. So they wanted it just that that A randomly. So n equals 1 in this case. So that's going to give me here. So this probability is going to be 0.4280. This one coming down here, it has dropped significantly. All right, let's try it again with the better one here. Sorry about that. So suppose that a geyser, if you don't know what a geyser is, you can Google that. They're really cool looking actually. Has a mean time between eruptions of 94 minutes. So here's my mean. Let the interval of time between eruptions be normally distributed with a standard deviation of 27 minutes. So here's my standard deviation of 27. What is the probability that A, that means n equals 1, randomly selected time interval between eruptions is longer than 107 minutes? Well, let's draw that out. Mean is 94. 107 minutes, that'll be over here somewhere. So this will be 107 to 99999. The mean of 94, standard deviation of 27. So this is just 1, n is 1 in this case. So you could even say it's 27 divided by the square root of 1. We don't normally put that, but you could. So here we go. Norm CDF, 107, comma, 999, 94, 27. 0.3151. So 1 going off longer than 107, not that unusual. 32% chance that would happen. But if the mean of, in this case, 8 of them were to be longer than 107 minutes, that would be much more unusual. So this is going to be norm CDF of 107. By the way, this means that our new standard deviation is going to be 27 divided by the square root of 8. Here you can see our standard deviation was just the 27 from above. 4, and now again directly into the calculator, 27 divided by the square root of 8. I will put that directly into there. Seven, 94, and then 27 divided by the square root of 8. And you can see that has changed quite a bit. Lot less chance of that happening. What is the probability that a random sample of 29 time intervals between eruptions have a mean longer than 107? Now that it's gone up, that's going to be way lower. So now our standard deviation is 27 divided by root 29. And now it's 27 divided by root 29. That's gone down significantly lower. That is using the central limit theorem, folks.